Okay, so this is going to be the notes for section 2.4, part 1 or part A, which is specifically linear application problems. Okay, which basically means just real world applications that you can use the equation of a line to represent. So sometimes applications can model a linear relationship, meaning have a linear equation. So for example, suppose Mrs. Teapot decided to record the growth of her son Chip every 3 months. Sounds a bit like Beauty and the Beast, doesn't it? When he was born, he was 19 inches tall. Okay, so notice age, it would be times 0. So that's when he was born, he was 19 inches tall. And then it says exactly 3 months later, so 3 months is your age, he was 21 inches tall, and so on. So here's the growth chart. Consider the ordered pair, age in months, comma, height. So it's like 0, 19 would be an ordered pair, or 3, 21 would be an ordered pair, and so on. So part A, what is his growth rate, or slope, for the first 3 months? So we would say his slope is, well, don't you subtract your y's? And remember, we have this is our x, this is our y. So wouldn't it just be 21 minus 19 all over 3 minus 0? So that comes out to be 2/3. Now, because it is a real-world application, we want to include units. And so since the y values are on top, that's the height. And remember, the height is in inches, so inches. And on bottom is months, so that would be inches per month. So every month, he grows 2/3 of an inch. Okay, part B. What is his growth rate for the 3 to 6 month time period? Okay, so here's the 3, here's the 6. So now we want the slope between those 2 points. So m equals 23 minus 21 over 6 minus 3, which is also 2/3. Again, the y value is inches, and then the x value was months, inches per month. So the same growth rate from 3 to 6 months as it was from 0 to 3. And what is his growth rate for 6 to 9 months? So, oops, sorry. Here's your 6 ordered pair and your 9 ordered pair. So the slope is 25 minus 23 over 9 minus 6. Again, 2/3 inches per month, which if we thought about it, we would have known that these are all going to be the same, because remember up here at the top it says we're talking about a linear relationship. So since the slope remains the same for all the data, this is a linear relationship. And so think about it, on a line, isn't the slope the same all the way from one side of the line to the other? The slope doesn't change, the slope stays the same everywhere on a line. So if your slope or your rate of change is the same, you know it represents the equation of a line. Okay, write the linear equation for Chip's height in terms of his age. So remember, the height is the y values, and the age in months is the x values. So we would say y equals, the growth rate, the slope was 2/3. So we're thinking mx plus b, right? So 2/3 x. And so what's the plus b? Well, we know it's a y-intercept, right? So it's a y value, but what specific? Well, didn't we say that a y-intercept always has an x-coordinate of 0? So he was born at 19 inches, so it's like that's our beginning height. That's our y-intercept, so plus 19. And if I really wanted to make this be an application problem, instead of using y and x, I might have said h for height equals 2/3 m for month plus 19. If this relationship remains linear throughout his life, how tall will he be when he is 2 years old? Well, 2 years old, wouldn't that be 24 months? And remember, so if I put in 24 for m, I would say height equals 2/3 times m, so 24 months, plus 19. And if I want to do the math, let's see, 3 goes into 24 8 times. So that's 16 plus 19 is what is that, 35 inches. So we're saying when he's 2 years old, he's about 35 inches. That makes sense, a little less than 3 feet when you're 2 years old. That sounds about right to me. Do you think it's reasonable that a person's height and age will remain a linear relationship? In other words, for their entire life, would it follow this same equation? I think the answer's got to be no for a lot of reasons. Because think about it. Have you ever heard someone say, oh, you're going through a growth spurt, which means you're growing faster now maybe than you did earlier? Or the other thing to think about is at a certain point, don't we stop growing? And so we don't continue to grow, which means we're not going to keep getting taller at the same rate every month. So I definitely think this is a no. Whoops, sorry. Definitely think this is a no. Okay, let's try another example. The body length, y, in inches of a walrus, okay, so the length of a walrus can be modeled by this equation, where x is the calf. A baby walrus is called a calf, where x is the calf's age. So we're still measuring, I guess, how long instead of how tall these walruses are based on how old they are in months. So remember, the y is the height and the x is the number of months. So what do the slope and y-intercept represent in this graph? Well, it's true that the slope is 5, and just like up above, since we're talking inches and months, that would be inches per month, and so that means the walrus is going to grow 5 inches per month, right? What about the y-intercept? Well, the y-intercept is 42. Y-intercept is 42, and remember, since we know it's the ordered pair 0, 42 times 0, right? So that would be the beginning length of the walrus, like when they were born. Use the equation to estimate the body length of a calf that is 10 months old. So we want to let the x equal 10, right? Because that's the months. So y equals 5 times 10 plus 42. So that would be 92 inches. So after 10 months, a walrus is 92 inches. I don't know if that's accurate or not, but I do know walruses can get pretty big, pretty long. Okay, what is the age of the walrus? So I want to find x. Remember, age is x. I want to find x if it is 200 inches long. So basically the y is the 200. Well, remember the equation up here. Y equals 5x plus 42. But this time we know the y is 200, and we're trying to solve for x. So let's see, I'll subtract 42. So 158 equals 5x, and this would be a calculator problem. So divide by 5. So x equals, let's see, 31.6. Put that in your calculator and check. So that means we're saying it would be 31.6 months before they get to be 200 inches long. Okay, so that's the first part of section 2.4.